Hello, my name is Andrew Brooks. This is another presentation of Non-Linear Existentialism, Modulating Amygdala Activities, subtitle Summarizing Limbic Regulation. These are the various parts of the presentation. The gist of this is just giving more detail for amygdala and how they, more finer points, specific areas if I can, of the system and how it regulates positive and negative feedback regulation in the system as theorized under non-linear existentialism. We've had the variable being monitored, controlled, and it's then you have the sensor, then you have the integrator, then you have the set point. For this one is the primary needs baseline activity level, which I theorized is in the hippocampus. And then the effector, and that's in the amygdala. These are the variable reinforcement curves. The blue ones mirror each other, and just shows that the increased amount of reinforcement output for stronger positive and or negative. But this is perfectly symmetrical. There's going to be, of course, asymmetrical conditions. And again, the idea is that a positive or negative pattern or energy produced by it is going to be only reinforced if it increases probably the set point, which is going to be the primary needs baseline activity level. This is just the interplay of them and showing different conditions that each pattern can have. And there can be a multitude of patterns, so of course there's going to be possibly a multitude of variable reinforcement curves. And throughout this, it's taking the non-optimal one's baseline activity level towards the primary needs baseline activity level. So one thing to go over is the interplay of variable reinforcing curves, a little bit more information. Level of excitation of the internally processed stimulation sent to the CA3, which is a pacemaker in the hippocampus, is a function of the current state of variable reinforcement curves within stable patterns of the hippocampus interacting with new input. It should be noted that inhibitory cerebral output could become excitatory in the contextual environment of the hippocampus and vice versa. Because we're talking about the hippocampus, this is going to be the long-term or stable patterns as opposed to the dynamic patterns that are present in the cerebral cortex. The effector, and what I've done is this, these are when they are italicized, and when I had them beforehand they were italicized. And this is kind of, we mentioned this a few times, so I just italicized it for emphasis. So in this one, it's mentioned if the level of excitation is to be increased, the amygdala potentiates the cerebral patterns that are created, and if the level needs to be decreased, the amygdala inhibits the cerebral patterns that formed it. The question is, what does potentiate mean, and how is it accomplished? Basically, it can be accomplished in two ways. Potentiation means to strengthen, so it can strengthen by increasing the amount of excitation to it, to the patterns, the patterns that are formed within the neuronal tissue, or the length of time of that excitation. So it can be a lot of energy over a short period of time, or a little bit of energy over a long period of time. They should do the same thing. So this is just a very basic overview of the pattern. This is going to be the large loop going from the cortex through the hippocampus to amygdala and back up again. And through the rest of the presentation, I'm just going to fill in the details of this. So the idea I'd like to think of, I like to work in metaphors and similes, is we think of the sensory input coming into the cerebral cortex or the sensory modalities as kind of idea of keys on a piano. Again, that draws up the idea of sound, but this could be to any type of sensory input. So striking a particular key gives it a particular energy that goes through the lines in the key, in the piano, and those are brought down, that energy is brought down to a centralized area for the for the cerebral cortex, that would be the hippocampus. And if you get associations between those vibrations on the lines, and if they stay there, that would be long-term memory. And so just kind of like there, we have individual components being brought together and stored. And the issue, of course, is that you don't want to have the individual keys glued together, and that's why I theorize that in the cerebral cortex there's this dynamic component, so those keys don't necessarily get glued together. Sometimes they do, sometimes they don't. So from there, the activated cerebral channels pathways sensor from the cortical area sends neuronal signals, variable being modified, controlled, into the hippocampus. Part 2, stable pattern region of the hippocampus. Input interacts with the stable stored patterns in the body of the hippocampus, the integrator. Due to the interaction of specific and interconnected variable reinforcement curves, various neuronal patterns with associated level of neuronal energy can and are produced. Number 3, output to the CA3 from the stable patterns. Again, we're within the hippocampus still. Summated energy difference between non-optimal wants baseline activity level and primary needs baseline activity level. This is going to be the set point. Within stable storage is produced. Energy level difference is a function of the complexity and stableness of the patterns activated within each of the groupings. And again, we've got many, I'm not sure, untold amount of groupings within the long-term memory stable patterns. And each one of them are going to have their own outcomes, and then when they come together, we have an output, which in this case is going to be the CA3. This is important. I'm going to give a visual to this very shortly, but when there's a high difference between the non-optimal wants baseline activity level and the primary needs baseline activity level, there's going to be a decreased discharge of frequency of the CA3. The reason being is that if they're far apart, then being the primary focus of this is going towards primary needs baseline activity level, there is a computation within the system that says, well, this isn't reaching their goal or set point, so therefore we're going to decrease discharge frequency for it. And the discharge frequency is going to be a pulse, and in this case it's a pacemaker cell, and this is going to be CA3, has a pacemaker area within similar to the heart. The proposed relationship is similar to the CA node and the vagus nerve. The CA node has a baseline discharge frequency of 60 to 100 beats per minute. Again, I'm not sure what the baseline level is, and it's going to be set, as I mentioned, the early part of a person's life. So it's going to be unique probably to the individual. So given that, so again, high difference, decreased discharge frequency of the CA3, median difference, no change in the discharge frequency, and low or no difference, increased discharge frequency, again, because it's the non-optimal wants baseline activity level is very, very close to primary needs baseline activity level, and of course the system wants to reinforce it. Break it down even further. So if you're going to stay in the CA3, that node, decreased discharge frequency of the pacemaker, low potentiation, there's no reinforcement, no maintenance. Directly to the cortex, medium discharge frequency, moderate potentiation, maintenance. The amount of energy that's produced isn't enough to produce a new patterns. What it does is just maintain the previous patterns, hence the name. And into the amygdala, then to the cortex, this is where the effector is, effector being enforcement. High discharge frequency, high potentiation, we have reinforcement. So you can see overview here, you got number 1, number 2, number 3, number 4, and 5 and 6. 4 basically stays there. The lines from the CA3 going back to the hippocampus, again, it's just because the primary needs baseline activity level, does not change. It does not mean it cannot vary. So if the primary needs baseline activity level needs to if there needs to be communication back to hippocampus, those lines kind of indicated recurrent systems or return pathways are occurring. And if you see at the bottom there where I see stable patterns, it just shows you the difference between the orange line and the blue line. Orange line where it wants to go to, this is the baseline level. I could have put in where it varied up and down, but I decided not to. That just get too complicated, but understanding the primary needs baseline activity level, and this one's the baseline for that one, but it can vary up and down. And below the blue, that's the non-optimal wants baseline activity level. That's one's hopefully throughout a person's life being drawn up to primary needs baseline activity level. And ED is the energy difference. So the thing is that the further apart the lines are, the less likely the system is going to reinforce it. And if we go for number 5 being maintenance and number 6 being reinforcement. Another thing about this presentation, I just wanted to bring up things that when I was reading through the work and just checking things out to see if there's no contradictions. I don't think there are. I just wanted to clarify some things. So the first thing I want to clarify is point 1. If energy output from the amygdala is proposed to reinforce neuronal patterns which invoke them, does that then imply that if there are initiating patterns that reduce cerebral excitation, would then stimulating and reinforcing such patterns alter them, and thereby decrease the neuronal initiating fidelity? Long and short of it is, if the area is negatively, it's caused a negative output in the unstable dynamic cerebral patterns, and then going through the system, and then the system decides it needs to be reinforced, and reinforcement's usually considered positive. Would a positive cause the initial negative condition to become positive and reduce infidelity? Point 2. Again, this is where I kind of italicized it to show, give reference to where I took it from. So the idea is, if the level needs to be decreased, the amygdala inhibits the cerebral patterns that formed it. Given this statement, how is this a positive feedback loop? Shouldn't a positive feedback loop always increase the variable? You would think, but again, I'll address that shortly. Number 3, if a person experiences a sensory event with a negative energy signature, and the non-linear existentialism appears to claim that this would lead to no reinforcement of the initiating event, and hence no memory formation, why do people remember such negative events in the short and long term? Okay, hopefully these will clarify, and these are apparent answers. By the amygdala modulating the time function potentiation that is increasing the length of time the input is sent to the pattern to reinforce it, it would be theoretically possible not to alter the level of excitation that invoked an initial input into the hippocampus. The idea being there's energy sent to it over a long period of time, but the amplitude of the energy isn't so much to change it from its initial negative or positive condition. Number 2, inhibiting or not reinforcing patterns that decrease non-optimal once baseline activity level is not contrary to a system that has evolved in continually increasing non-optimal once baseline activity level. In other words, there is no inhibition of the variable that the positive feedback loop is designed to continuously increase. Furthermore, inhibiting or not reinforcing that which decreases non-optimal once baseline activity level actually increases the variable. So the idea is that if there is inhibiting or decreasing, it isn't of positive, which a positive feedback loop would want. Essentially, the excitation is going to be that which could decrease it. So I think that holds true to what a positive feedback loop would be. Number 3, while the theoretical dynamic energy exchanges occurring within and between the cerebral patterns are supposed to continuously and temporarily stabilize unstable patterns, some of which may become stable, the limbic system attempts to bring non-optimal once baseline level to primary needs baseline activity level. So they have two different, they go towards the same idea, but one is more contextual. That would be the stable patterns in the limbic system, and whereas for the cerebral cortex is stabilizing an unstable condition temporarily. As a consequence of this, while short-term negative as well as positive cerebral patterns may extinguish due to new instability being generated by the frequency amplitude modulation through V1B, such patterns may also become long-term patterns within the cerebral cortex only if there is sufficient reinforcements from the limbic system to stabilize it in that environment. Such activity will also further increase the stability of the transferred patterns within the hippocampus. For example, a short-term negative event, pain from touching a hot object, can become ingrained and contextualized if such a pattern ultimately increases the non-optimal once baseline activity level. So the gist of it is that the instability in the cerebral cortex cannot be considered in the same light as a stable contextualized system in the hippocampus, but they don't interfere with from either one of each other, but they do ultimately can go towards the same outcome. So I thank you very much for your time and for your patience in this matter. Again, it's a lot of information, and I would just say that anyone who's interested in this material is go through it, and if they have any questions, please contact me. Thank you very much.